You all. I am Dr. C. Jagan from Rogani College of Engineering and Technology, Associate Professor, Electronics and Communication Department. So this video I have discussed about ad hoc wireless sensor networks.
Spacecraft technology structure. A satellite communication system can be broadly divided into two segments, a ground segment and a space segment. The space segment will obviously include the satellites, but it also includes the ground facilities needed to keep the satellites operational, these being referred to as the tracking, telemetry and command TT&C facilities. In many networks, it is common practice to employ a ground station solely. The equipment carried above the satellites also can be classified according to a function. The payload refers to the equipment used to provide the service for which the satellite has been launched. In a communication satellite, the equipment which provides the connecting link between the satellites transmit and receive antennas is referred to as the transponder. The transponder forms one of the main sections of the payload, the others being the antenna subsystem in this chapter. The main characteristics of certain bus systems and payloads are described. The power supply. The primary electrical power for operating the electronic equipment is obtained from the solar cell. Individual cells can generate only small amounts of power, and several arrays of cells in series parallel connections are required. Figure shows the solar cell panels for the HS-376 satellites manufactured by Hubs Space and Communication Company. In geostationary orbit, the telescoped panel is fully extended so that both are exposed to sunlight at the beginning of life. The panels produce 940 watts DC power, which may drop to 760 watts at the end of the 10 years. During eclipse, power is provided by the two nickel cadmium NICD long life batteries, which will deliver 830 watts at the end of the life. Battery recharge time is less than 60 hours. Capacity of cylindrical and solar cell satellites. The crossover point is estimated to be about 2 kilowatts, where the solar cell type is more economical than the cylindrical type. Attitude control and orbit control. The attitude is a satellite refers to its orientation in space. Much the equipment carried aboard a satellite is there for the purpose of controlling its attitude. Attitude control is necessary, for example, to ensure that directional antennas point in the proper direction. In the case of Earth environment satellites, the Earth sensing instruments must cover the required regions of the Earth, which also requires attitude control. A number of forces referred to as disturbances torque can alter the altitude. Some examples being the gravitational fields of the Earth and the Moon, solar radiation, and meteorite impacts. Attitude control must not be can focused with the station keeping, which is the term used for maintaining a satellite on its correct orbital position. Although the two are closely related, to exercise attitude control, there must be available some measures of satellites orientation in space, and of any tendency for this to shift. In one method, infrared sensor referred to as horizon detectors are used to detect the rim of the Earth against the background of space. With the use of four such sensors, one for each quadrant, the center of the Earth can be readily established as a reference point. Usually, the attitude control process takes place about the satellites, but it is also possible for control signals to be transmitted from Earth based on attitude data obtained from the satellite. The yaw axis is directed toward the Earth's center, the pitch axis is normal to the orbital plane, and the roll axis is perpendicular to the other two. B or By axis for the geostationary orbit. Here, the roll axis is tangential and to the orbit and lies along the satellite velocity vector. The three axes which define satellite's attitude are its roll, pitch, raw axis. These are shown relative to the Earth in figure. All three axes pass through the center of gravity of the satellites for an equidistant orbit. Movement of the satellites about the roll axis moves the antenna's footprint from the south. Movement about the pitch axis moves the footprint east and west. And movement about the raw axis rotates the antenna footprint. Spinning satellite stabilization. Spin stabilization may be achieved with cylindrical satellites. The satellite is constructed so that it is mechanically balanced about one particular axis and is then set spinning around this axis. For geostationary satellites, the spin axis is adjusted to be parallel to the ns axis of the earth as illustrated in figure. Spin rate is typically in the range of 50 to 100 revolutions per minute. Spin is initiated during the launch base by means of small gas jets. In the absence of disturbances torques, the spinning satellite would maintain its correct attitude relative to the earth. Disturbance torques are generated in a number of ways, both external and internal to the satellite. Solar radiation, gravitational gradients, and meteorite impacts are all of example external forces which can give rise to disturbances torques. Figure above figure spin stabilization in the geostationary orbit. The spin axis lies along the pitch axis parallel to the Earth's ns axis. Overall effect is that the spin rate will decrease and the direction of the angular spin axis will change. Impulse type thrusters or jets can be used to increase the spin rate again and to shift the axis back to its correct orientation. Nutation, which is a form of wobbling, can occur as a result of the disturbance torques and or form misalignment or unbalance of the control jets. This nutation must be dammed out by means of energy absorbers known as nutation dampers. The antenna feeds can therefore be connected directly to the transponders without the need for radio frequencies RF rotary joints. While the complete platform is despond, of course, controlled signals and power must be transferred to the despond section and a mechanical bearing must be provided. The complete assembly for this is known as the bearing and power transfer assembly BABTA. Figure 3.4 shows a photograph of the internal structure of this HS-376. Certain dual spin spacecraft obtains spin stabilization from a spinning flywheel rather than spinning the satellite itself. These flywheels are termed momentum wheels and their average momentum is referred to as momentum spacecraft HS-376 spacecraft. Momentum wheel stabilization. In the previous section, the gyroscopic effect of a spinning satellite was shown to provide stability for the satellite's altitude. Stability also can be achieved by the utilizing the gyroscopic effect of a spinning flywheel, and this approach is used in satellites with the cube-like bodies such as shown in the figure and the Intelsat V-type satellites shown in the figure. They are known as body stabilized satellites. The complete unit termed momentum wheel consists of a flywheel, the bearings assembly, the casing, and an electric drive motor with associated electric control circuitry. The flywheel is attached to the rotor, which consists of a permanent magnet providing the magnetic field of motor action. The starter of the motor is attached to the body of the satellite. Thus, the motor provides the coupling between the flywheel and the satellite structure. Speed and torque control of the motor is exercised through the current fed to the starter. When a momentum wheel is operated with the zero momentum bias, it is generally referred to as reaction wheel. Reaction wheels are used in the axis stabilized system. Here, as the name suggests, each axis is stabilized by a reaction wheel as shown in figure. Reaction wheels can also be combined with a momentum wheel to provide the control needed. Random and cyclic disturbances torques tends to produce zero momentum on average. However, there will always be some disturbances torques that causes a cumulative increase in wheel momentum and eventually at some point of the wheel saturates. In effect, it reaches its maximum download allowable angular velocity and can no longer take in any more momentum. Mass expulsion devices are then used to upload the wheel, that is remove momentum from it in the same way a brake removes energy from a moving vehicle. Of course, operation of the mass expulsion device consumes part of the satellite supply. Thank you.